Dear students, in this video, I am going to discuss multi-step methods. So in this category, we will discuss two methods. One is Adams-Bashforth method and another one is the Adams-Moulton method. Okay, so what is first? What is basically the multi-step methods? So what is our problem? Problem is just dy by dx is equal to f of xy, a function of x and y, where y is the dependent variable and x is the independent variable, and with the condition is y at x naught is equal to y naught. So basically this is an initial value problem. So these methods, multi-step methods, uses past values of either yx or derivative of f of y or both of them to construct a polynomial that approximates the derivatives and extrapolates into the next interval. Okay, so the meaning is that we are having data in terms of we will use the data in terms of y or y dash x to construct a polynomial. So basically we will approximate this function f of xy with the help of the interpolation. Okay, so here is the data, here is this range. So here is meaning that past data means we are having, for example, past data from xn minus k plus 1 nth point to the xn point. So these are total k number of past data points, and we are trying to predict the value of y at point xn plus 1. That means we are aware about the value of yn here, yn minus 1 here, yn minus 2 here, and up to yn minus k plus 1. So we are already aware about these points, and the target is to predict the value at this point, that means yn plus 1. Okay, so these past k data points is already known to you, or either you can have given to you. Okay, so now, so generally multi-step methods can be written as, because we have already told that to find the value at this point we will use the values this, we will use the derivatives as well as yx, past values of yx, past values of derivatives. Okay, so that's why the multi-step method is basically the function. So we are target is to predict the value at this point, so yn plus 1, which is approximately equal to a1 yn, that means this value, plus a2 yn minus 2, that means this value, and so on, plus a3 yn minus 2 and so on, and last one will be this value ak yn minus k plus 1 plus h, some function phi of these independent variables xn plus 1, xn minus k plus 1. That means we are included this point also, and the derivatives, because we have already utilized these points yx from here to here. Now we will utilizing the derivatives, so that's why the independent variable as well as the derivative values y dash n plus 1, that means the derivative at this point, y dash and y dash n minus 1, y dash n minus k plus 1, that means derivative up to this. So we are utilizing the derivative at this point, this point, this point, and up to this point. Okay, so we are utilizing all this data. Now since phi is not known to you, so basically for simplicity we will take the linear function, and hence this yn plus 1 is approximately equal to from here to here as it is same value plus h times this linear function, that means a1 yn this plus a2 yn minus 1 up to ak yn minus k plus 1, that means these term as it is same plus h times the linear function. So in place of this we will have the linear function of the derivatives. So h b naught y dash n plus 1 this plus b1 y dash and this plus b2 y dash n minus 1 and bk y dash n minus k plus 1 last. Okay, so this is question number 1. In summation form this can be written, this part is written here, summation I from 1 to k ai y n minus I plus 1, and this part is written here h summation I from 0 to k, because here b naught to bk. So that's why I starts from 0 to k bi y dash n minus I plus 1. This is equation number 2. Okay. Now here, because you don't know about y n plus 1 and you are here writing y dash n plus 1, so this may be difficult for you, and hence we have two cases. Either this b naught is non-zero or b naught is 0. If b naught is 0, that means we are removing this term, and hence we will get yn plus 1. This is exactly equal to a1 yn plus a2 yn minus 1 plus ak yn minus k plus 1. That means the terms from here to here plus h times, this is 0 because b naught is 0. So we will start from b1 y dash n plus b2 y dash n minus 1 and so on plus bk y dash n minus k plus 1, this term. And this is known as explicit. Because why this is explicit? Because in the right hand side you can see that there is no term of y n plus 1 or its derivative. Only y n plus 1 is in the left hand side. However, here you can see that here we have the derivative in the right hand side at point n plus 1. Okay, so herein in explicit form there is no n plus 1 in the right hand side. That's why this is explicit, because this is free from y dash n plus 1. And as an example, if you take k is equal to 2, that means here we will take only two past data points, and two past data points is nothing but xn and xn minus 1. Put k is equal to 2 here, so we get n minus 2 plus 1, that means n minus 1. So we have only two past data points. That's why formula will be yn plus 1 is equal to a1 yn plus a2 yn minus 1 plus b1 y dash n when k is 2. Fine. Now, when b naught is non-zero, then this is known as implicit. Implicit because right hand side contains y dash n plus 1, which is according to this is nothing but a function of xn plus 1 and yn plus 1. So in which yn plus 1 is still unknown, because we are trying to find out yn plus 1, and that yn plus 1 is in the right hand side, and hence क्योंकि जिस चीज को हम निकालना चाहते हैं वही right hand side में है, that's why this is implicit. Okay, herein there is no yn plus 1 in the right hand side, that's why this is explicit. But herein we will have y dash n plus 1, and since we know that y dash n plus 1 depends upon xn plus 1 and yn plus 1, that's why in the right hand side we will also have yn plus 1 in indirect form, and hence we can say that this is basically the implicit. Okay, here just an example, again we are taking k equal to 2. So when you put k is equal to 2 in this equation, so we will get yn plus 1 is equal to a1 yn plus a2 yn minus 1, because we will have only two past data points, plus h b naught this y dash n plus 1 plus h b1 y dash n. Okay, because here we will have n minus 2 plus 1, so ultimately n minus this. Okay, so we will have this term. So I think you have some sort of idea about this. So this is just an example. So now here we will have these are the general explicit scheme. This is the general implicit scheme. Now here we will study only two methods. One is Adams-Bashforth method, which is basically an explicit method, that means of this category, and Adams-Moulton method, which is basically an implicit method, that means of the second category. Okay, so let's see what is the procedure. So first we will discuss about the Adams-Bashforth method, which is an explicit method. So here the problem is y dash is equal to f of xy, and initial condition is y at x naught is equal to y naught. So this is the data xn minus k plus 1. We will aware about the value of this point, that means yn minus k plus 1. Similarly, this point will be xn minus k plus 2, next point, and similarly and so on up to xn. So all these data, xn means corresponding value is yn, which is also known to you. So these past k data points is already known to you. Target is to find out the value of y at this point, that means yn plus 1, and the step size between two consecutive x is h. So k known past data points we have. The target is to find out yn plus 1. So now integrate this equation with respect to x. with limit xn to xn plus 1 from here to here. Okay, so integrate. So when you're integrating this part, so we will get only y with limit xn to xn plus 1 is equal to, now integrate the right hand part, so integral xn to xn plus 1 f of xy dx. Now this will give you yn plus 1 minus y, and then when you take minus yn in the right hand side, so we will get this. So yn plus 1 is equal to yn plus this part, so integral xn to xn plus 1 f of xy dx. This is equation number suppose 2. This is 1, this is 2. Now to evaluate f of xy in 2, we can approximate f of xy by a polynomial that interpolates f of xy at k data points, past data points. First point is this xn yn, this. Second is xn minus 1 yn minus 1, this, and so on. And last point will be this pair xn minus k plus 1 to yn minus k plus 1. For this we shall use Newton's Gregory backward interpolation. So this is very important. To approximate, to interpolate this f of xy with the help of these past data points, we are using Newton's Gregory backward interpolation. Okay, of degree k minus 1, because we have how many points are there? Total k points there. So obviously the degree of the polynomial will be, interpolating polynomial will be k minus 1. So if f has k constant derivatives, then what will be the formula for Newton's Gregory? You are already aware about the formula, I think. All of you are very much aware about that. So now you applying the Newton's Gregory backward interpolation. So this is f of xy, which is approximately equal to a interpolating polynomial denoted by k minus 1th degree. This is the degree of the polynomial, depends upon x. So this is equal to fn. Fn means value of the function at last point, because if you are aware about this, let's see. Let's see the table. Here is this, because last point is basically what? xn, yn, and corresponding f of n. Okay, then next point will be xn minus 1, yn minus 1. Here we will start with this, because this is backward Gregory. So n minus k plus 1, n minus k plus 1. This is n minus k plus 1. Then n minus k plus 2, n minus k plus 2, f of n minus k plus 2, and so on. And last point will be xn. So this is xn corresponding y, and then f of n. So now we will find out the first difference. So this will be the nabla f of n, and so on. And here we will have nabla f of n minus k plus 2. Last point will be from here to here. Similarly, the second order difference, because we will, you all will, आपको पता ही है कैसे निकालते हैं difference. So this is starting from this. So backward means we are moving in this direction, okay. So hence this is basically this f of n, last point, then x minus x, because this will be the center point, this will be your center, last point. So x minus xn upon h, first derivative difference, nabla, this nabla f of n, plus then x minus xn, and then previous point will be x n minus 1, corresponding value will be y n minus 1, f of n minus 1, and then this difference will be f of n minus 1. So that's why x minus xn minus 1 divided by factorial 2 into h square, and then nabla of second order fn, and so on. And this will be the second last point, x minus xn minus 1 up to x minus xn minus k plus 2. That means this point divided by k minus 1 factorial h raised to the power k minus 1 nabla k minus 1 fn. And this is the last term corresponding to the starting point, x minus xn minus 1, x minus xn minus k plus 1 divided by factorial k and f of k. Here we don't have this, because this is the error term. This is basically the error term. So here we will not have the difference, because if you will see in the last column, we will have only up to the order this. last order difference will be this kth minus 1th order difference. So this is the error term basically. The derivative of f, k times derivative at point xi, where xi is some point in between n minus k plus 1 to xn. That means in between this to this range, any point. Okay, so this is basically the error term, and this is due to the Taylor series. This is due to the Taylor series. I think you are already aware about the Taylor series. So this is basically the expansion of Taylor series, and this is the last term, error term. Okay, now let us assume this x minus xn by h as a new variable u. So then dx will be, when you differentiate this, so left hand side gives you du and the right hand side gives you dx upon h, because this is a constant, xn is a constant, h is a constant, only variable is x. So du is equal to dx by h. That means dx is equal to h du. This is equation number 3rd. Okay. Now when you find out the next one, because this x minus xn by h is already u. Now in this term, if you will realize this, that x minus xn minus 1 divided by h square. So you can take one h with this term and another one h is with this term. So ultimately x minus xn minus 1 by h. This part. Now replace this x with the help of this. You can find out x. X is nothing but uh plus xn. So that's why xn plus uh. Minus of this term, so minus xn minus 1 divided by this h. Okay, so when you divide this, so this term will give you u, and xn minus 1 divided by h is this. And now since the consecutive difference between two x is h, so xn minus 1, obviously the difference will be h by h. So ultimately this gives you u plus 1. So ultimately what we can do, what we are trying to say, that you are replacing this quantity by u, then this quantity, because one h is with this term, another h is with this term, so this term will be nothing but u, and this term is denoted by simply u plus 1. So ultimately we will have u into u plus 1. In the next term we will have u into u plus 1 into u plus 2 and so on. Okay, so that's why this polynomial pk minus 1 is nothing but fn plus u into this, u into nabla this, plus this is, now we will have u into u plus 1 divided by this factorial 2, and second order difference u into u plus 1 into u plus 2 divided by factorial 3, and third order difference, and so on. And in the last term you can see that there is no h in the denominator. However, in all the rest of the terms you can see that in the denominator we have h. So first we will multiply by h raised to the power k here and divide by h raised to the power k here. That's why here we have h raised to the power k. Okay, and then this, and the remaining strategies as it is same, u into u plus 1 into u plus 2 into u plus k minus 1 divided by factorial k. So since we have multiplied here h raised to the power k and divided by h raised to the power, the division is basically managed by this u into u plus 1. However, the multiplication is written here. Okay, तो जो डिवीजन में आएगा वो तो u को मैनेज कर देगा, u उसको मैनेज कर देगा, लेकिन जो प्रोडक्ट वाला है वो ये रहा, h raised to the power k f k xi. Okay, so this is basically the point. Now replace this quantity herein, put it herein, and then what we will get this yn plus 1 is equal to this, yn plus 1 is equal to yn plus this integral. And now when you put the lower term xn, lower limit herein, when you put the lower limit x is equal to xn, then xn minus xn will be 0. That's why lower limit will be 0. When you put the upper limit xn plus 1 herein, so xn plus 1 minus xn is basically h by h is 1, hence upper limit is 1. And now this is replaced by this expression, this polynomial. So this is this polynomial, and then here we have dx, but here dx is h du, so that's why h du. Okay, now you can take this h constant in starting position here, and then now integrate this. So because now the variable is u, that's why u fn, plus when you integrate this with respect to u, you get u square by 2 nabla fn, plus similarly integrate this, we will get u cube by 3 plus u square by 2 divided by factorial 2 nabla to f of n, and so on, with limit 0 to 1, 0 to 1. And after solving this, we will get this value, which is yn plus 1 is equal to yn plus h fn plus half nabla fn plus 5 by 12 nabla 2 f of n plus, and so on. Okay, so this will be the general formula. Now, depending upon your k, past data points, so this is basically the general Adams-Bashforth method with order. K decides the order. Number of past data points decides the order. So if your k is 3 past data points, then what will be the exact formula? If your k is 4, then what will be the formula? So here is this. So if you are using k is equal to 3, that means we are using past 3 data points xn, corresponding value of yn, xn minus 1, yn minus 1, and xn minus 2, yn minus 2. So we are using these 3 past data points. Okay, and then we will first interpolate our polynomial with the help of this pair. So ultimately construct the table. X column is this xn minus 2, xn minus 1, xn, these data points. Then corresponding value of y is yn minus 2, yn minus 1, yn, and then the corresponding value of f is fn minus 2, fn minus 1, and fn. Now the first difference is this. So obviously this will be nabla fn minus 1. Second order difference will be this, nabla to fn. Okay, so now replace this where? In this equation, or just simply use this last formula. If you will see, in the last we have got this. So since our table, according to this table, we reached up to second order difference, that's why we will use up to formula here in only up to this. तो क्योंकि हम सेकंड ऑर्डर तक पहुंचे हैं, तो अगर आप इसको पुट करेंगे अपने फॉर्मूले में, इस इंटीग्रल में, तो फिर पूरे प्रोसेस फॉलो करेंगे, देन वी विल रीच अप टू द सेकंड ऑर्डर डिफरेंस ओनली. अप टू केवल यहीं तक आएगा, थर्ड ऑर्डर डिफरेंस नहीं आएगा, जीरो हो जाएगा. ओके, सो दैट्स व्हाई द फॉर्मूला विल बी y अप टू दिस, yn plus 1 is equal to yn plus h, first difference yn, then this term, so this term, and then this term. So this, that's why मैंने केवल यहीं तक लिखा है, because हम second order difference तक ही calculate कर पाएंगे. Okay, and the error will be order of h raised to the power 4, and this is decided by the error term. If you will see this, k is just 2, in our case k is 3, so this will be h raised to the power k, that means h raised to the power 3. Okay, when you integrating and multiplying by this h, so ultimately this product will give you h raised to the power 4. That's why this is h order of h raised to the power 4, error term. Okay, this is the error term. Now just substitute the value of nabla fn and second order difference. So fn yn plus h fn plus half nabla fn is nothing but the difference between these two. So fn minus f of n minus 1 plus 5 by 12. Second order difference is nothing but the difference between these two. But this is nothing but this, the distance between fn minus fn minus 1, and this is nothing but nabla f of n minus 1 is nothing but fn minus 1 minus f of n minus 2. So when you use this, ultimately this is the second order difference, fn minus twice of f of n minus 1 plus f of n minus 2, and this is the error term. So ultimately when you simplify, so we will get this formula, yn plus 1 is equal to yn plus h by 12 23 fn minus 16 f of n minus 1 plus 5 of n minus 2 plus order of h raised to the power 4. So ultimately Adams-Bashforth method of order 3, order of 3 means k is equal to 3, is given by this formula, yn plus 1 is equal to yn plus h by 12 23 fn minus 16 f of n minus 1 plus 5 of n minus 2, and the error term is of order raised to the power 4, which is this. So this term is basically in expansion form. This order of h raised to the power 4 means this 3 by 8 h raised to the power 4 f of f3 xi. This is the error term. Okay, so this is the Adams-Bashforth method of order 3. Similarly, when you take 4 data points, so now we are using past 4 data points xn, yn, xn minus 1 yn minus 1, xn minus 2 yn minus 2 and xn minus 3 yn minus 3. So we have to compute up to third order difference. तो अब हम हमारा एक डिफरेंस एक बढ़ जाएगा एक, दैट्स वाई दिस फॉर्मूला इन प्लेस ऑफ नाउ दिस, जब हम इसमें रखेंगे इस फॉर्मूले में तो नेक्स्ट टर्म भी हम इसमें यूज करेंगे थर्ड ऑर्डर डिफरेंस, विच विल बी बेसिकली द 3/8. हियर we will have 3/8 third order difference and so on. Okay, so we will use this third order difference. So now yn plus 1 is equal to yn plus h fn plus half nebula fn plus 5/12 nebula 2 fn plus 3/8 nebula 3 f of n. एक ऑर्डर बढ़ जाएगा यहाँ पर, तो ये बढ़ गया, प्लस ऑर्डर ऑफ h रेज टू द पावर 5 हो जाएगा. लास्ट टर्म में यहाँ रखेंगे k इज इक्वल टू 4, k is equal to 4, h raised to the power 4 multiply by h, so h raised to the power 5. So the last term is basically this order of h raised to the power 5. Okay, again replace the value of these differences, first order, second order, third order, and obviously we know that these differences follow the binomial expansion. So that's, so fn, so yn plus h fn plus half of this is nothing but fn minus f of n minus 1 plus 5/12. Second order difference follows the binomial expansion, so that's why this is fn minus twice of fn minus 1 plus f of n minus 2 plus this 3/8, and the third order difference, which is this fn minus 3 of fn minus 1 plus 3f of n minus 2 minus f of n minus 1 plus this array term. So when you simplify, so this will give you y of n plus 1 is equal to yn plus h by 24, 55 f of n minus 59 f of n minus 1 plus 37 f of n minus 2 minus 9 f of n minus 3, and this is the error term T40, truncation error hai this, that's why this is denoted by T. So 251 by 720 f of 4 xi h raised to the power 4. This is Adams-Bashforth method of order 4, and error is of order 5. Here the error is of order 4. Adams-Bashforth मेथड ऑर्डर 3 का है, जबकि इसकी जो एरर है वो ऑर्डर 4 की है. सिमिलरली दिस इज Adams-Bashforth मेथड ऑफ ऑर्डर 4 एंड इट्स एरर इज ऑफ ऑर्डर 5. ओके, so similarly you can find the formula for k is equal to 5, k is equal to 6 and so on. So this is basically the Adams-Bashforth method. Now in the next video we will discuss the Adams-Moulton method, which is an explicit method. Okay, thank you.